Okay. You guys watch the time. Make sure so I can reset this if it goes over. This should only take a short period of time.
So if I talk, it can hear me now?
We'll talk.
Can you see the writing on the board?
Yes, very clearly. When you go on YouTube, it's wonderful. It's like YouTube, you're there.
So people are going to hear me on YouTube?
Seriously.
I'm gonna do my best Spanish accent.
All right. Okay. Now, so far we've talked about. Let me make a little argument of why vectors are important. Okay. Maybe that's escaped you guys, which is fine because I don't think we mentioned it. If I'm talking about two objects moving relative to each other. Now remember, I'll use it a little example. If there's a Mr. Manus sitting in this rolling chair here, I know it doesn't look like I'm sitting, and I have a twin that's identical sitting in this chair, and we push off of each other. What does Newton's second law say about the momentum of that situation?
They'll be equal.
It'll be the same before and after. The fancy word for that, if I'm looking at both of these as part of the system, the fancy word for that is conserved. So if the two people are just sitting here, and momentum, I'm going to define as mass times velocity. If those people are just sitting there, what's their momentum if their velocity is 0?
0.
0. Does that make sense? So then, if their momentum is 0 before, and momentum is always conserved in a closed system, that's a system where stuff is not allowed to come in or go out, what would the momentum be afterwards? By Newton's second law? 0. Does that make sense?
Yes.
So, no?
Yeah.
Yes? No? That's all. Newton's postulating this. By postulating means like he's just shaking his arm and saying this is the way it is. Okay? There's no deriving this. He's just saying that it's so. Because you can look at and see it in nature. That's a good reason to postulate it. Okay? So let's check it out. So this is a fancy way of just saying adding up all the momentums. So Pi, how many different momentums is in this thing right here? 2, yeah. So it's just P1 and P2. These are adding, right? Well, how do they cancel out to give you 0 if they were scalars, if they were both plus? Could they cancel out? No, they can't. So the only way that this works is if this is vectors. So adding up all the momentum vectors in the beginning was easy because it was mass times 0 plus mass times 0. Does everybody follow that? That's from my definition, because from my perspective, looking at the board, nobody's moving. So the momentum is 0. Now, Mr. Newton said before and after, it's got to equal. So mass 1, that'll just be, the masses are going to be equal. So, and velocity 1, and that's a vector, plus mass 2, which is the same as mass 1. So I won't put subscript there because they're equal. That this together equals 0. Now the only way that can happen is if they're in opposite directions, because there's a plus symbol there. Does that make sense?
Yeah.
Now these are simple vectors in one dimension. Remember, what's the only thing you have to worry about when a vector's in one dimension? Well, yeah, that's given because it's a vector. You always have to worry about direction in a vector. But what's the only thing that indicates the direction?
Do it.
The what? I said this before. It's the sign, right? Like if this wasn't a vector, if you took away the fact that it's not a vector, v1 equals the negative of v2. Notice I took away the vector symbol. But this would be true too, because you're just pulling this side of the equation. But that's what gives you the direction, because the only thing that can happen to vectors in one dimension is it can flip 180 degrees. How do you flip a vector 180 degrees? You stick a negative sign in front of it. Or if it's negative, you multiply it by -1 and flip it back the other direction. Does that make sense?
Yes.
Okay, all right. Now, that's not as nice. What if we have a pool ball and a pool cue, but it doesn't hit it center mass? Say it hits it on the side, what's going to happen to the pool balls? One will go this way, and this one will go what way? Now can you use one dimension to analyze this problem? No. You have to consider not just the x component, but the y components too. What is the momentum? The momentum before the ball collides. It's not 0 because this ball is moving.
Oh, they're talking about that.
No, this is the whole picture. Newton didn't say the momentum was 0. He just says it's the same before and after a collision. He says it's unchanged, does not change over time. It's conserved. Yeah? Does everybody get that? Okay, so what's the momentum? This is velocity 1. Somebody help me. What did I say? What's the definition of momentum? So then what's the momentum? You can do this. Multiplication. If you know the velocity, can you find the momentum? And if you know the mass, what do you do to them? You multiply them together. So the momentum is just mass times velocity. Now somebody you might say, Mr. Manus, please plug in some numbers. Get over it. You're big boys now. No more pull-ups. Time for real bloomers and real chonies. Big boy pants. Right?
Yeah.
Okay. He knows what I'm talking about. Okay. So, is it 0?
No.
What direction is that vector going to be pointing? Sorry, I put a P there. What direction is this momentum vector going to be pointing? To the right. Is there any y component to this vector? No. So after the collision, is there any y component?
Yeah.
No.
No.
You would be violating Newton's. You would be changing the momentum, right? Because you're saying now that there's a y component. Well, how is there not a y component? It's a tricky question. Don't feel bad. Why is there not a y component after the collision?
Does it stay the same?
It does stay the same, but that's circular reasoning because I said it has to stay the same. But why does it stay the same is the question. Well, not exactly. I think you're on the right track. What is the y component? Notice that they're equal. Do you see that? So what's going to happen to these two different y components?
They cancel out.
They cancel out and you're still just left with the same old momentum that you had in the beginning. Do you see that? Now what if you hit it funky like this? To where it goes off at a shallow angle like this. What has to happen to this ball? It goes at a strong angle up, right? If this is a shallow angle, is momentum still conserved? don't know. It depends on the velocity, right? What that means is this one is going to have to be going very slowly in the y direction. So I'll redraw the arrow. That's the y component, right? So that means its new y component is going to have to be very tiny. And since this has a huge x component, it's not going to be taking, it's not going to have very much x left either, right? So what'll have to happen is you have just a tiny little bit. So basically, the ball will just take off in a much slower direction, right? Now, what if the ball hits it square? Then this vector goes away altogether, and this ball is left sitting there, not even moving, right? And then that ball takes off with its momentum, and that ball is stationary for the same mass. Have you guys seen Newton's cradle? Those balls that's what's going on, is the mass is just getting traded off. But in order for mass to be conserved, if it hits it along the center line, like if it hits it straight along, boom. Then there's not going to be any y component. That means this has got to carry away all that momentum. And this is going to stop, because the momentum can't change from the beginning to the end. It's got to be conserved. So now do you see the purpose of why now we're going to have to use two components? You guys believe, is that convincing? Yeah? Okay. So let's make it go back to the easier stuff. If I have a vector that points out in that direction, now hopefully you understand why it's not necessarily pointing in the x or y direction. Because you saw that if you're treating cue balls, heads up, Tobias. Are you okay? All right. Yeah, keep your head up. I'm working hard over here. Please pay attention. All right. So if you see that, and you saw that in that example, if you're going to treat cue balls, you have to have x and y together. So this is pretty easy. Like I said, don't overlook it. Now, this right here, the length of this vector is r, right? Now, there's two ways you can talk about a point in space. Two ways that you've probably learned in school. Maybe you haven't learned this one, but you're going to anyways now, if you haven't learned it yet. With this arrow, can you touch every point in this x and y plane? I'm going to say yes, because you could change the angle, and you could change the length of this r vector. That r, that means the length of it. Let's just put it that way, just the vector. And let me see. Okay, if the ground is x and y, right, and I'm a sprinkler, what can a sprinkler do? The little kind of sprinkler. Can it rotate every angle? Now, if I have just pretend I got a sprinkler that can rotate every angle. Is there any reason why this can't do 360 degrees? No, there's not. Did you have a question? Okay, so now this is a special sprinkler. I could turn it up with infinite water pressure. Now pretend that space is, the earth is actually flat and it goes on forever. And there's just a little bit of, well, it doesn't matter, it could be whatever gravity, but if I could shoot out the water with infinite pressure, can I hit any point in space? Yeah, because I can make this vector longer by increasing the pressure. What if I want to hit just right in the origin? What do I do?
Decrease it.
Yeah, decrease it all the way to 0. So it just drips out. Okay, so now with XY, everybody already knows that in XY you can use Cartesian coordinates to pick out any point in space, right? So now the only task you have to do is convert them. Because what I'm saying is, if you want to build a vector using this is called polar coordinates. You can build a vector you can use Cartesian coordinates and just tell somebody, here, I'll write it here. You just tell somebody that, say, for point 1, it's at x3 and y4. And you just say the tail's at the origin. Now, once you build this vector, can you move it around? Yes, as long as it's pointing in the same direction, you don't make it longer or shorter, it's the same vector. It can go anywhere it wants to afterwards. But when we're constructing them like this, using the XY coordinates, you put the tail at the origin and the tip goes out somewhere to some point in space that you define, that you say. So then you have an X component, which is 3, and a Y component, which is 4. Now, I can make a vector like this. We'll call it vector A is equal to 3x hat plus 4y hat. What's this x hat 4y hat business? What's the x and y hat business? You guys know what that is?
It's when it's positive.
That's what?
It goes X direction and then
Yes.
it goes Y direction.
Why do I have to put these here? There's 2 reasons actually that I put these here. Give me one of them and I'll tell you the other one. Yes, that's one reason. Because this is a little notation telling you that it's pointing in the x direction. What's the magnitude of that little x hat guy?
3.
It's just 1. It doesn't change the length of the vector, right? It just tells it what direction it's going. So now this is a real vector. What if I didn't have this? If I just had 3 plus 4, would A be a vector? No, that's stupid. A would be 7. Because now these terms are alike. What can you do in algebra when you have like terms? You can add them up. Are they like terms now?
No.
No. You can add them, and they also have direction. This one has direction in the x direction. This one has direction in the y direction. So now it's a vector. You see that? Now what if you were going to add it to a vector b, and say vector b is 10 in the x plus 3 in the y hat? How would you do that? Can you just add them? Why not? But can't you collect these terms? Yeah. Then you get a c vector that equals 13 in the x direction plus 7 in the y direction. You see how that works? Is that complicated? No. Okay. That's all we're going to be doing. But here's one thing: is a lot of these vectors you're not given. This is in Cartesian form. Some of these vectors are given to you in polar form. So what that means is instead we're gonna give you that the length is 5 and the angle is 30 degrees. So say this is a length vector. We'll say it's 5 meters. Can you turn that into a component, a Cartesian vector? How would you do that with algebra, a little trick? If you know the hypotenuse, how would you find this? And what I like to call this is a projection. Because if this is a ruler, like say the sun is high noon, and you got this ruler out, you can say what's the projection on the x-axis of the ruler? How long would it be? This is a meter stick. How long would that projection be? The shadow underneath the yardstick.
Well,
It'd be 1 meter, right? It'd be the same. Would that be true if I start moving it up like this? What's going to happen to it? It's going to shrink. Do you guys know what it is when it's 60 degrees? It's half. Unit circle. What about when it's at 30 degrees? Square root of 3 halves, yeah. What about when it's at 45 degrees? Yeah. Square root of 2 over 2, yeah. And that's, if you actually measured it, you would get that exact length as long as the sun's straight overhead. So if I say projection, that's what I'm talking about. So you could say this vector's projection on X is this. What part of what trig function do you use to find the adjacent side? If you know the hypotenuse.
Cosine.
Cosine. So then here's our vector. A, you guys are writing all this down, right? Okay. A equals the magnitude of A, which is just its length. That would be 5 meters. Here, I'll do the example first so you don't get confused. So 5 meters times cosine of this angle here. I'm not going to write in the angle, just so I keep it nice and generic. Plus, oh, you can't forget it. What if I forgot to put the x hat? I'd be messed up, huh? Because then I could add them, and you're not supposed to be able to do that. So x hat plus 5 meters. What function goes here to find the y? This is what side? What part of the triangle is this? This is adjacent. What's this guy?
Opposite.
Opposite. What trig function do I use?
Sine.
Sine. Look, I already started writing. You could have cheated me. Y hat. So then to calculate this guy, we know that the cosine of 30 is going to be, that we already discussed that. That's going to be 1/2. So then the answer is 5 meters over 2. Right? Yeah. And that's in the x direction. This is still A we're talking about. Plus 5 meters times pi over a third. I mean, sorry, not pi. Root 3 over 2 times 5 meters times y hat. And that's our answer. We just converted that to polar. You guys see that? What if you want to go backwards? What if you want to convert this to, what if you want to convert this to polar? How would you do that? How would you find this length?
Should we find the slope?
Just the Pythagoras theorem, right?
Yeah.
3 plus 4, this would be 9 plus 16, that's 25. What's the square root of 25? That's just 5. Look, so then I know that, right? Now how do I find the angle here? That's a harder question. Not impossible, but it's a harder question. How do I find the angle? What trig function would give you that angle? Tangent would give you the ratio. If you knew the angle, it would give you the ratio of these two angles. But we know the ratio. So what would you need to do, the tangent, to get the angle back? What would you need to do?